Hello and welcome to another episode of the Geotechnical Engineering Podcast. On today's episode, we'll be talking with Dr. Matt Evans, who is a professor of civil engineering at Oregon State University. We'll be talking about geotechnical engineering as a profession and how it relates to really everybody's life here on the planet. We'll also be talking about the crucial role that technology plays for the advancement of geotechnical engineering as a profession. I'm your host, Jared Green, and I'm excited to be bringing you another episode of the Geotechnical Engineering Podcast. But before we get started, we're going to hear a word from today's sponsor, that being PPI, a Kaplan company.
Before we dive in, we'd like to recognize our sponsor for this episode, PPI, a leader in engineering exam prep for the FE and PE exams. PPI provides expert prep courses and study resources designed to help you pass the FE and PE exams the first time. PPI's live online courses include hours of lectures, problem-solving demonstrations, exam strategy sessions, office hours, and a passing guarantee. Check out PPI today at ppi2pass.com to see all the options available for FE and PE exam prep. Now let's dive into today's episode.
All right, Dr. Evans, how you feeling?
Good, thanks, Jared. Good to be here.
Excellent. I really appreciate you being here on the show. We see each other at conferences and committee meetings, and I've always thought in my mind, it'd be great to get you on the show and just have you talk a little bit. So I appreciate you carving out some time for us today.
Well, thanks for having me. I really appreciate it.
Excellent. Well, I would love it if you could tell us a little bit more about yourself and what is it that you do on a daily basis. Let us know how you got to where you are and what it is that you do, just to set the stage a little bit for us.
Sure. So, as a wee lad, I got a degree in a bachelor's degree in physics, and didn't get a lot of traction in the physics world. Ended up going back to school studying geotechnical engineering, or studying civil engineering, I guess. And then I practiced for a few years. In the late 90s in Southern California, decided that I preferred research, went back to school for a master's and PhD, and I've been in academia since about, 2006, first for a few years at NC State, and then for the remainder of my career here at Oregon State University. And my responsibilities on a day-to-day basis are teaching, research, and the way I know you, service to the community and the profession.
Excellent. I appreciate that. And what led you to specialize in geotechnical engineering, within the broad field of civil, especially with the physics background? I mean, how'd you land here?
It's funny that physics does play into that a bit, but also that geotechnical engineering kind of found me. When I went back to school for civil engineering, I decided to get a bachelor's degree because I didn't know what I wanted to do, and so I figured I'd get a bachelor's degree in civil engineering, and so I'd get to see geotechnical and structures and hydraulics and a bit of everything. Well, I was at the University of New Mexico, and my first semester, they made me take statics. And I tried to make the argument that, I've kind of seen all this before, and I don't think it would be helpful for me to take this class. And they said, well, you don't have a class on your physics transcript that you can point to and say that class is statics, so we need you to take it. So I took it, and I did learn some things. It was a good class, but I did pretty well in it because I had seen a lot of it before. The person teaching the class is a guy that I still consider a friend today, John Stormont, a geotechnical professor at UNM. And at the end of the term, he said, you did pretty well in my class. I'm looking for an undergraduate researcher in my lab. Would you be interested? And I went to a geotech lab and found that I really liked it. I like the uncertainty. I like the fact that every problem, every project is a little bit different in geotechnical engineering. No two soils are the same, and it just sort of stuck for me.
That's great. And in the end, it ties back to physics, right? So
Exactly.
It's kind of good background there. And now, how did your passion for civil engineering and physics help shape your career path into academia?
For sure. I kind of cut my teeth as a young researcher. I was an undergraduate research assistant as a physics major. I was an undergraduate research assistant as a civil engineering major. The firm that I went to work for, Geotechnical Consultants in California at the time where I was, there were a lot of people in that office that had PhDs in geotechnical engineering. They were research minded. And, this was sort of a part of my career from the very earliest stages. And at some point while I was a practicing engineer, I realized that I enjoyed that part of it. It was pretty cool designing things and then watching them get built, of course. But at the same time, the thing that excited me the most was research. And so that's kind of what brought me back to academia and then to pursue my master's and PhD. And when I left practice, I very specifically, I was actually working for Ed Kavazanjian at the time. And I talked to Ed and I said, I'm thinking about going back to school for a master's degree and a PhD. And he said, well, you really don't need to do that unless you want to be a professor. And I said, well, about that. And so that's kind of how we, how we got here.
Oh, that's great. That's great. Yeah. It's like, do you need it? It's like, well, if you're on this route, you need it, right?
Exactly.
I love it. Can you talk about a recent project that you worked on that highlights the impact of geotechnical engineering on our daily lives?
One thing I think that people have gotten awful excited about over the work that we've done over the last 5 or 6 years, and this is work that I've done in collaboration with my my good colleague here at Oregon State, Armin Studline, on the liquefaction resistance of some of the native Oregon silts. And these are no to low plasticity silts that are oftentimes 99-95% passing 200. They're very fine grained. And under a lot of kind of existing metrics, we might expect that these silts aren't liquefiable. And I think that's kind of the way that they've been viewed in Oregon for an awful long time. But when, we start testing intact specimens of this material, when we start doing blast-induced liquefaction in situ, Ken Stokey and Brady Cox were out here with TRX. We did some shaking. We start to see that under the right conditions, these can be liquefiable materials. And that's particularly true when we start thinking about a Cascadia subduction zone event. We've got a subduction zone that's just a few tens of kilometers off the coast of Oregon that, when it ruptures, we're going to have, we have the potential for magnitude 9 shakes with ground motions that last for minutes. And so under that type of loading, these materials very much are liquefiable. And, that kind of changes the way we think about how we do geotechnical engineering in Oregon, that, we need to be moving forward in a way that appreciates this liquefaction potential of our materials. And so, our hope is that this is research that kind of directly informs, retrofits, future construction in the state, and hopefully leads to increased seismic resilience for our state.
Oh, that's great. I mean, the reality is that if formerly you thought a material could not liquefy or would not liquefy, and now you have results that are showing otherwise, that changes the state of practice. It's pretty powerful. Let's see. So how did the principles of physics integrate into your geotechnical engineering research and teaching?
Sure. From a research standpoint, we tend to oftentimes in my group like to think about things from first principles, right? We appreciate the fact that we need to do some continuum analyses. There needs to be some empiricism because, frankly, right now anyway, soils are just too hard of a problem to have an exact closed form solution for, right? We need Terzaghis observational methods still, but, we try to inform that with first principle science. And from a teaching standpoint, I come at it kind of the same way. I think that sometimes in some of our civil engineering, our approach to some of our undergraduate classes, where we teach students to do a small subset of things kind of very, very well. But when I think about the way that undergraduate physics classes were approached when I took them, it was very much about, building a toolbox. We're not going to teach how to build a table. All we're going to do is we're going to teach how to use a hammer and how to use a screwdriver and a drill and a sander and a saw and what have you. And then at the end of the term, maybe you can build something with it. Maybe you want to build a table, maybe you want to build a chair, but you're going to have these tools. And so I try to use that paradigm to inform the way that I teach some of my classes, is that, we're not going to just spend our lectures doing, example problem after example problem, and then I'm going to ask you to repeat those problems on homework assignments. But instead, let's strike some balance between, theory, application, case studies, examples, and let's see if we can, learn this pretty robustly from the first principles to the actual practice.
I really appreciate that. I hope that your students appreciate that as well. I mean, to study just to get a good grade on a final it's not what learning is all about, right? So
no,
getting that
not at all.
Getting that toolbox so that you can then build something, I think is a very powerful notion as an instructor and a professor. So what would you say is the most significant change that you've seen in civil engineering education during your time as a professor? And I can imagine that post-COVID that even it probably changed even more. But what are some of your thoughts here?
And that feels almost like a cop-out answer, but the thing is that, far and away, the biggest change I've seen is this post-COVID understanding that there are different ways that we can deliver courses, right? And but before COVID, and it's not as if the technology in 2021 was a lot different than it was in 2019. All the pieces were already there. But, in 2019, pre-COVID, let's say, if I've got to travel for a week to go to a conference or whatever it might be, I'm either trying to do extra lectures before I go to keep the classes caught up, or I'm doing extra lectures when I get back, or I'm finding one of my really excellent PhD students, hey, could you please, teach this class for me? But the idea of that I could just give the actual lecture and record it and leave it for the students, or I could even do the lecture live from wherever I'm traveling to. For me, anyway, it was a pretty foreign concept. I'm sure some of my more enlightened colleagues were doing these sort of things ahead of time, but now it's kind of the norm. And, it really changes the way that I deliver my classes. I've got, where I feel like I've got some more flexibility. Sometimes if I don't get to something in class, I'll record a short video after the fact and say, hey, this will help you with the homework. You might want to watch this 5-minute video, or, but whatever it might be. The thing that I'm seeing changing more slowly, but I think for the better, is civil engineers moving away from tools like Excel and towards tools like MathCAD or Python or MATLAB. I know that some of these software, like MATLAB, has a very high barrier to entry. The cost is substantial for a consulting firm, let's say. But it's not the case with Python. When we look at things like MathCAD, where we have or Maple, where we have this WYSIWYG type interface. To me, it feels like these things are not only more powerful than Excel, but they're more transparent.
Yeah.
It's not just a table of numbers. You can see the calculations that are behind the numbers. It makes the calculation packages easy to check. Makes the homeworks easier to grade from my standpoint. But that's a movement that I've seen us making slowly. But it does seem like we are making it, that there are better tools than Excel to design things.
That's great. You touched on this a little bit before, but let's dive into a little bit. How does your work at Oregon State University contribute to solving real-world engineering problems?
That's one thing that I really like about our program here at Oregon State, and about the things that we value as a school, as a faculty in civil engineering, is we have got tremendous relationships with local consulting firms, local contractors, all sorts of local businesses. We're very OSU and the College of Engineering in general are very entrepreneurial. We have great relationships with state regulators, the Department of Transportation, and as such, we're able to really solve problems that are of direct influence to our community, and hopefully the broader community. But we often start here in Oregon. We've done this work with liquefaction of silts. We're doing ongoing work now with the Department of Transportation, where they've had problems with designing structures that come in contact with deep diatomaceous deposits, where the engineering properties are difficult to predict. Liquid limit's 150, but the drain friction angle is 42 degrees. So real counterintuitive type behavior, and we're helping them navigate some of those complexities. And we've done some work that we think is has direct application that's not even actually civil engineer, or geotechnical engineering. My work really, the theoretical part of it is granular physics. And we did a lot of work a few years ago on powder spreading for 3D printing and additive manufacturing. And so things that people really do get to pick up and touch. We think we were able to improve the way that some people do those processes. And so, it's through these relationships with local companies, local consultants, contractors, that we're able to work on not just kind of ivory tower type problems, which are fun too, but also problems that we feel like, touch people's lives, or that, touch the communities around us.
That's great. I wasn't even thinking about powder spreading as granular physics, but it is, right? It's no different from the work that was done, with grain silos, right? It's like,
yeah, exactly.
It's just a different scale. So that's really awesome and very practical too. Very practical.
It is.
So let's see. What role do you believe that technology plays in the future of geotechnical engineering?
Well, again, I think that I said earlier about the biggest change in COVID and remote delivery feels like kind of a cop-out answer. Well, I guess the cop-out answer for this is AI, right?
There you go.
I think that's, it feels like it's the thing that everybody's talking about right now. But, it's something that it's real, it's coming. And GPUs, programming on GPUs makes this sort of stuff very, very fast. And it's the type of stuff that, I think sooner rather than later, we're going to see it trickling into engineering design and practice. I think that a concern with that is that when you ask these large language systems, or these large language models, or however these things are trained, big complicated questions that you don't really know the closed form answer to, how do you test the result? How do you know they're giving you the right answer? And I like to tell this story of I teach an undergraduate class that touches on slope stability. And when you start thinking about things like wedge failures, and so, you've got to, you get these complicated trigonometric equations. You got to take the derivative and set it equal to 0 to find the critical wedge and all this. Well, you get these long trigonometric functions that are hard to really, make intuitive sense of. And so I asked ChatGPT, I had one of these long expressions. I said, could you please simplify this for me? And it gives me a simplified answer. And I plot my original, and then I plot the simplified answer, and they're not the same.
Yeah.
And so I ask it again. It gives me a second answer, also incorrect. I do this 5 times. It gives me 5 wrong answers. And I think that practicing engineers are probably, careful enough that they would do the similar types of checks. But for undergraduate students, for example, they might not be, right? They're just, computer said that's the answer. I'm going to turn it in.
Submit.
Mm-hmm.
Wow. So we got some work to do there. Just to make sure we understand why we're doing what we're doing, right?
Yes, absolutely. And make sure that we can believe the answer.
Yeah. Excellent. Well, that sounds like a good piece of advice, but I'm going to give you an opportunity for another piece of advice, final advice for engineers just starting out in their career. So these could be folks that are in consulting or folks that are taking the academic route. What's some advice you have before we take our break?
I think that there are a couple of things. Work hard. That's easy to say. A big thing is make yourself valuable. Don't pigeonhole yourself. I think that a lot of times we say, well, I want to be the slope stability person, or I want to be the discrete element method person, or the finite element method person, or whatever it might be. But make yourself valuable to your employer. And it keeps things interesting for you as well, right? Learn how to do different things, and be good at them. Take pride, and I think that's the type of thing that not just in geotechnical engineering, but in any job that keeps you engaged, keeps you employed, and makes it so that when you get up in the morning, you might not always look forward to going to work, but you don't get up every morning dreading it, right? Yeah. That you go in, you say, I'm going to work with good people, and I'm going to solve hard problems, and I've got some variety ahead of me.
It's excellent. It's excellent. Good note to pause on. We're going to come back in just a minute and close this one out with Matt in our Career Factor Safety End segment. Stick around. All right, welcome back. It's time for our career factor safety end segment. In geotechnical engineering, just like many disciplines of engineering, it's important to incorporate a factor of safety into your design. But what about incorporating a factor of safety into your career? Today, of course, we're speaking with Dr. Matt Evans from Oregon State University. Now, Matt, you've already had a very successful career. When you look back on your career, what's something that you've implemented in your career to give yourself what's called a factor of safety in your career?
Sure. I think the biggest thing, Jared, is to keep learning, right? We are a young field, right? What are we, 100 years old, maybe, give or take? And, we think about the way we did things 100 years ago or 50 years ago, or even 10 or 20 years ago, are so different than what we do now. And I think that it's so important to not stagnate, to keep learning, developing new skills, learn new models, learn new programming languages, learn new construction techniques, learn new whatever it might be. But and as long as you're not stuck doing things that were appropriate 10 or 20 or 30 years ago, and instead thinking about learning what you need to know to solve problems appropriate ways in the next 10 to 20 to 30 years, I think you're going to have that factor of safety, right? You're going to remain valuable.
Excellent. Well, Matt, thank you so much for coming on and sharing all the great insights with us. You shared some great information and advice I know is going to be helpful for our listeners and those that are watching. If somebody wants to reach out to you, what's the best way for them to get you? Are you on social media, website you want to share, email address we can get in the show notes?
For sure. I've got a Twitter handle. It's at @TMatthewEvans.
Okay.
And also my email at Oregon State's a great way to get me, and that's matt.evans@oregonstate.edu. And unfortunately, I'm probably Googleable too.
There you go. Well, thank you so much for coming on. This is really great. It's really great.
Thanks so much for having me, Jared. This has been fun.
I hope you enjoyed the episode today. We would love to hear your feedback, comments, and or questions. Please feel free to go to geotechnicalengineeringpodcast.com, where you'll find a summary of the key points discussed in today's episode, as well as links to any of the resources, websites, or books mentioned during this episode. Until next time, we wish you the very best in all of your geotechnical engineering endeavors. Peace.